In podcast 25, I want to introduce you to the concept of work and energy. So firstly, take a look at these two signs here. Very similar signs. One of them makes sense, one of them doesn't. Now, number one hopefully makes sense. It's correctly oriented because we can see a person on a slope pushing at a ball. And they're having to push on the ball because they're pushing it uphill. 2 doesn't make sense because, as you know, you don't have to push a ball downhill. But why not? And the answer is, of course, gravity. But we need more of an explanation than that, and it's all to do with the concepts of work and energy. Now, both of these words are commonly used in the English language. You've all used them, and a student may say, for example, "Oh, I had so much work to do last night, I didn't have the energy to do it, so I went to bed." So is the student using these words in the correct scientific context? Well, the answer is really yes, in fact. The sentence indicates that the student needs energy to do work, and that is a good definition of energy. It's scientifically correct. But where does the energy come from? And what actually constitutes work in a scientific sense? So let's develop or look at some definitions. Now, going back to the person on the sign, here's the person again. It's very clear that the person here is working, they're doing work, they're working hard to push this ball uphill against the force of gravity, against the weight of the ball. Heavier the ball is, the harder it is to push up the hill. As the ball moves up the hill, it gains energy. The higher up it goes, the more energy it's got. And I know this because if the ball is released from a greater height, it will roll down the hill and it will reach the ground at a higher speed. V will be greater if we drop it from a higher height. But where does the energy that the ball has actually come from? So the energy comes from the person. And where does the person's energy come from? It comes from the food you eat, so that you have energy to do work. So doing work is actually the process of taking energy from one place or thing and giving it to another. It's actually the transfer of energy. And by now it should be clear that without energy you cannot do any work at all. If something has energy, then it's actually got the ability to do the work. So the person has energy, and as a result of that they can do work. They can transfer their energy to the ball, and the ball gains energy as it moves up the hill. So in this example here, how much work is being done? So let's look at a simplified scenario. So I've taken away the hill, and instead of having gravity as the resisting force, I've got friction in here as the resisting force. So the person here is pushing the block with a force, the red arrow, equal to the red arrow, and friction force is acting against it. Hopefully you can identify that the resultant force on the block is 0, so when they push the block it will move at a constant speed. So let's move that block through a distance S. There we are. The person just pushed the block through a distance S. So when this person moves the force through the distance, work is done. And the work is proportional to the force, and it's also proportional to the distance. If I double the distance moved, I do twice as much work. If I double the push force, because the object is heavier, let's say, then also it's going to double the amount of work I do. So work is actually the product of those two things. Work done is the force applied multiplied by the distance moved, or in symbols W equals Fs. Let's look back at the first example again. So the person is pushing the ball uphill against gravity, against the weight of the ball. The weight of the ball, gravity, the gravitational force on the ball, is pointing downwards. So the movement against gravity is upwards, it's the vertical height moved. So if we relate that to the equation, we can see that we have W equals Fs, work done is force times distance moved, but in this case the force is the weight. We have to apply a force equal and opposite to the weight to get it to move upwards at a constant speed. And the distance moved is only the vertical distance moved, the height, because that's the direction of the force, the applied force. It doesn't actually take any work to move the ball in the horizontal direction if there's no friction involved. So the equation becomes work done is equal to weight instead of the force multiplied by height instead of the distance. But weight is actually calculated by multiplying the mass of an object by the gravitational field strength, or the force of gravity. So we've actually got this equation. Work done is equal to the object's mass times the gravity multiplied by the height that you move it through. So as you push it, you get tired, your energy is transferred to the ball, and the ball gains energy. And we call this energy gravitational potential energy. So the amount of energy, the amount of work done, is the energy transferred to the ball, and we call this gravitational potential energy. So we have this equation, E suffix P, for energy potential, gravitational potential, equals mass times the gravitational field strength multiplied by the height. G on Earth is close to 10, 9.81 newtons per kilogram. So let's imagine now the ball is released. What happens to the energy that you've put into that ball? What happens to that gravitational potential energy? So no prizes. You know that if you release a ball on a slope, the ball is going to roll downhill. As it gets lower and lower and closer to the ground, it's going to lose that potential energy, and that potential energy is going to be converted into moving or kinetic energy. Now we have an applet to look at from PHET, which clearly shows these energy transfers. So this applet has a slope here, and we have something being pushed. Now I've removed friction. You can see the object is on a skateboard, so friction is being removed. I'm not interested in the normal force really, or the weight of the object, but I'm interested in the push force. So I'm going to push just hard enough to get the crate to move uphill at a constant speed. So here we go. So up it goes. As it goes up, you can see the potential energy is going up. It's actually slowing down slightly, and I'm going to try and stop it when it's stop the animation when it has no moving energy. There we are. So the crate has now stopped moving. It's got potential energy, and it's actually got no moving energy at all. So what happens when I remove the applied force? So I'm going to remove the applied force. There is no force applied now. And when I start the animation again, we're going to see what happens. And I'll pause it there. So no surprises, the crate rolls down the hill. And you can see when it reaches the bottom, it's got no potential energy. It's lost all of that potential energy, and it's converted it into kinetic energy. You can see it has exactly the same amount of kinetic energy as it had potential energy at the top. So all of that potential energy was converted into moving or kinetic energy. So in summary, work is the transfer of energy. Energy, or having energy, gives something the ability to do work. If we do work against the force of gravity, we give something gravitational potential energy, or E suffix P. And when an object with gravitational potential energy is allowed to fall, this energy is transferred into moving or kinetic energy.